Should be page 38 in your package. So yes, this will be our last actual lesson where you're learning something new for this course. The good news for some of you, this course is offered again next year.
Wow.
Yes, we know who you are. Okay, so Tuesday then will be quiz on this stuff, and you'll get your review to start working on it for chapters 9, 10, and 11. We'll go through the quiz on Thursday. You'll have more time for the review, and then we will have your last exam class after that. So, but the diploma exam's coming up quickly, right? Friday, June 9th, 9 a.m. Still waiting to hear from Mr. Paquette. Or June 16th, sorry. Yes. 9 a.m. 9 a.m. Sorry. Still waiting to hear from Mr. Paquette because the deal is you guys are supposed to write in your classroom. However, I've got a 30-1 class that runs block 2 as well. You all can't be in the same room. There wouldn't be room. So I don't know what he's got planned, but he knows about it. So we'll wait for his plan about where the classes are writing. Pardon me? It's the first day of exam week. Yeah, our last day of classes is the 15th, and I don't think there's going to be much going on that day. I think Mr. Vobato's planning like kind of a barbecue kind of situation. Yeah, so you might get 60 minutes of class. Yeah. Okay, so we learned about binomial expansion. I showed you guys a fairly quick way that you can expand any binomial raised to any power. So that works. But we also talked about the fact that sometimes you're going to be asked for a specific term in an expansion. And so when that is what you're looking for, it's usually easier to use that general term formula that is on the formula sheet. It is T sub k plus 1 equals NCK. X, which refers to the first term of the binomial, to the power n minus k. Y refers to the second term of the binomial, to the power k. We learned that the k value is always 1 less than the term number. So if we want the third term, Miriam, what will k be? Caught you. I don't know. I'll play your silly game. Is it 4? K is 1 less than the term number, so 2. That sounds better than 4. Because if we want the third term, you want it to be term 3, so that k has to be 2. 2 plus 1 will give you 3. So n is 5. C, we've determined that k is 2. The first term in the binomial, I'm sorry, I'm looking at question C. Here, n is 6 for question B. So the first term is 4b, which is raised to the power 6 minus 2. And the second term, negative 5, is raised to the power 2. So 6c2, 4b to the 6 minus 2. B is negative 5 to the power 2. So 6c2 on our calculator is 15. 4b all to the power 4. Well, 4 to the 4 is 256. B to the 4th times negative 5 all squared, which is positive 25. So our coefficient is found by multiplying the 15 by 256 and 25. Oh, that's 25, not 22. Yeah. No, I'm not going to go backwards. I refuse to go backwards. There we go. 96,000. B to the 4th is the value of that term. Okay? Now, part C is going to require a bit more work. In the expansion of a squared minus 1 over a all to the power 5, so that would be the same as a squared minus a to the negative 1 to the power 5. Which term in simplified form contains a, which means a to the 1. We're looking for the term that will end up being the first degree term. So we're not told what the term number is. We need to figure that part out. We need to figure out what k is, which will tell us what the term number is. So we need to figure out what k is. I know that n is 5 though, so it'll be 5ck. The first term in the binomial is a squared, which is raised to the 5 minus k. The second term will be negative a to the negative 1, which is raised to the power k. This is what we know right now. Essentially, we only know what n is, and we know what the two terms of the binomial are. So I can do some simplifying here. There's a couple things that I'll do. Number one, first thing I'll do is inside this last bracket is negative a to the negative 1 all to the power k. This negative is the same as negative 1a to the negative 1. There are two factors here. The negative 1 is one factor. The a to the negative 1 is a second factor. They're both raised to the power k. I'm going to take the negative 1 to the power k and move it as my next factor because it's going to be used to get the coefficient. Then I will have a to the power. I can multiply these two exponents together, which is what you do when you have one exponent raised to another. It'll be 10 to the minus 2k. And then I've got a to the negative 1 raised to the k, which is a to the negative k, when you multiply negative 1 by k. Okay? Okay? Okay. So I can combine these last two factors together. You're multiplying powers with the same base. MJ, do you have gas, or do you have a question, or you're making this face? Okay, well, I, for one, am glad it's not the gas. So these last two factors, you're multiplying powers with the same base. You can add the exponents. So we have 5ck, negative 1 to the k, and then a to the power 10 minus 3k. When you add 10 minus 2k plus negative k, you'll get 10 minus 3k. Okay? We are looking for the term that has just a to the power 1. The exponent on a must be 1. 10 minus 3k must equal 1. Now we can solve for k. Okay? Subtract the 10. 1 take away 10 is negative 9. Divide by negative 3. Our k value is 3. It's actually the fourth term in the expansion. So now we can find out what that fourth term is by letting k equal 3. It'll be 5c3, negative 1 to the 3. and a to the 10 minus 9, which is a to the 1. 5C3 is 10 times negative 1 is negative 10a. So there's the term in that expansion that will be the first degree term, the term that will contain a or a to the power 1. All right? Looking at the next questions. How many terms are there in that expansion? Anyone remember? Yeah, there's one more. The number of terms is always one more than n. So the answer to question A will be 9. What is the value of the fourth term in that expansion? 2a minus 7 to the power 8. So it's the same binomial, the same power, but now we want to know what the fourth term is. So if we're looking for the fourth term, Sant, the value of k is? Yes. So it's going to be 8c3. The first term of the binomial 2a is raised to the power 8 minus 3. The second term, negative 7, is raised to the power k, or 3. So 8c3 is 56 times 2a all to the fifth. Well, 2 to the fifth is 32, a to the fifth, times negative 7 all cubed, which will be negative 343. And so we'll multiply the coefficients together. And get negative 614, 656. A to the fifth. There's the value of the fourth term in the expansion. You definitely could have used what we learned about binomial expansion and done the first 4 terms. But this is probably quicker. Maybe not, but then part C then asks us to use binomial theorem to find the first 4 terms in this expansion. So the first term, I think she's picking you up, but so the first term will be 7c0 to get our coefficient. The first term of the binomial 3a is raised to the power, well actually let's do it this way, raised to the power 7, and the second one 2b is raised to the power 0. Plus the second term will be 7c1. The power on 3a decreases by 1, the power on 2b increases by 1. Then we want 7c2. The power on 3a decreases by 1. The power on 2b increases by 1. And the last one, 7c3, because we want the first 4 terms. The power on 3a decreases by 1. The power on 2b increases by 1. Seven C0 is 1. 3 to the 7th is 2187. a to the 7th. 2b all to the 0 is 1. Times them by 1 changes nothing. 7c1 will be 7 times 3a to the 6th is 729. A to the 6th times 2b. Next coefficient is 7c2, 21. 3a all to the 5th is 243a to the 5th. 2b all squared is 4b squared. 7c3 is 35. 3a all to the 4th is 81a to the 4th. 2b all cubed is 8b cubed. So now we need to multiply coefficients together. Next coefficient is 10,206, and that's a to the 6b. The next coefficient will be found by multiplying 21, 243, and 4. 20,412. And that's a to the 5th b squared. Remember that whenever you add the powers together on the variables, they always have to equal n. They always equal 7. And the third term coefficient comes from multiplying 35, 81, and 8. 22,680. A to the 4th b cubed. So there is the first 4 terms of that expression. Okay? We talked about pathways before. How many different routes can a person follow? If they're going from point A to point B on a grid. So we saw that we could do this using basically talking about repetition, factorials with repetition. So one way to do this, if you're going from A to B, is count the total number of blocks. Remember, you don't start counting until you move. So starting at A, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 blocks total has to be traveled. So that could be done in 11 factorial ways. However, there's repetition because, and again, you don't start counting until you move. 1, 2, 3, 4, 5, 6 of those are going in the same direction. That's north to south. So you would divide by 6 factorial. And 1, 2, 3, 4, 5 are going in the same direction. That's west to east. So divide by 5 factorial. So this would be one way to determine how many routes a person could follow. So 11 factorial divided by, in brackets, 6 factorial times 5 factorial. Gives us 462 different routes, different pathways could be taken. Right? So that works. Now the thing about this method, it can only be used if the grids are full and complete. If we look down at part C, that grid is not full and complete. There's a piece missing. So that way of using number of roads are passed with repetition cannot be used for a situation like that. So we need a different method. And The different method that we can use is actually Pascal's triangle. Here's what that would look like. You're starting at A. So I'm going to put a 1 there at the corner. And you're also going to have 1s all the way along the top. So we're not counting the number of blocks you're traveling. We're counting the number of routes that you are taking. That's all part of the same route, going across the top. In the same way, going down the side is all part of the same route. A route doesn't change until you actually change a direction. So this is all part of the same route, going across the top or going across the side. This point right here, there are 2 ways to get there. You can go from A, you can go over and down, or you can go down and then over. Those are the 2 ways. To get to this point right there, there are 3 ways to get there. You can go over and down, that's the first way. You can start at A and go down and over, that's the second way. The third way from A would be going over 1 block, down 1 block, and then over. There's the 3 ways to get to this point right here from A. Now, if we continued the same process of actually counting all the individual ways, you'd lose count. You'd miss some of the paths, be a hard time to get the answer of 462 by counting. But if you look at the pattern here, this 2 can be found by adding these 2 1s together. 1 plus 1 equals 2. This 3 can be found by adding these 2 numbers together. 2 plus 1 is 3. The only way you can get to this spot where I have a 3 written is directly from above or from the side. If there's 2 ways to get to this point on the side and 1 way to get to the point above, that gives you your 3 ways. So you're just using the same pattern from Pascal's triangle. You're adding the 2 numbers directly above together to get the missing number. This point right here, you can only get there from above or from the left, so you're going to add those 2 numbers together. 1 plus 2 is 3. If I continue downwards now, 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5 is 6. There would be 6 different routes that you could follow to get from A down to this point at the bottom. Over and down is 1. Down and over is 2. And then there's also combinations of going down 1, then over, down 2, then over, down 3, then over, and then down. Those are all the different ways that you would do it. So we'll just continue now. To get to this point right here, you can only get there from above or from the left. So you're going to add those 2 numbers together. 3 plus 3 is 6. 4 plus 6 is 10, and so on. Continue on. $56 and 28 would be 78? No. 56 and 30 would be 86. Take away 2. 126 and that's 210. Is that right? And when you add 210 and 252, you'll get 462. Same answer we got using factorials. So the nice thing about this Pascal's triangle method is it can be used for all different types of pathway questions, whether they're full and complete or if there's pieces missing. Pardon me? What do you mean it wouldn't matter? It will matter. Huh? That's right. This can be used for any type of question. So, Question B, you're going from the bottom left up to the top right. Doesn't change the way it's done. We're starting at A, so along the side will all be ones, as well as along the bottom. We're just working upwards and to the right now instead of downwards and to the left. But we can just use Pascal's triangle. That same pattern of numbers. To get to this point here, you can either come from the left or below, so you'll add those together. To get to this point here, you can either come from below or from the left, so you'll add those two numbers together. And that pattern continues. To get to this point here at the bottom part of the that last line, you can either come from the left or below, so you'll add those two numbers together and continue.
What is that?
It's a drill. They're drilling. I think they're putting up some bulletin boards in some of the classrooms. So that's 120, I think. 84, 90 plus 30, yep. And 165. So 165 routes or paths could be followed to go from A to B. Which you could, this is using factorials. The other way of doing it is using permutations. No, combinations, sorry. To go from A to B, if you count the number of blocks you're going to travel, again, not counting until you move. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 blocks. 1, 2, 3 are going in the same direction. That would be from south to north. So you could say 11 C3, which, if you use the formula, is 11 factorial over 3 factorial, 8 factorial, which is what you would get if you did the way we first did part A, where we talked about repetition in both directions. Okay, so can also be done using combinations, which will lead you to that factorial statement that you would get if you said 1, 2, 3 are the same direction south to north. 1, 2, 3, 4, 5, 6, 7, 8 are the same direction west to east. Okay, so, but when you get to one like C, where you've got that tree in the middle that the person has to go around, we have to use Pascal's triangle for this. Okay, starting at A, moving to B. These will all be ones along here. Let me change the color. And going downwards, they'll all be ones along there. Again, this is the number of routes that a person can follow. Going across the top is all part of the same route, and that's what we're counting. We're not counting how many blocks they're traveling, it's how many routes they're taking. So the next row is easy to do, just like we have been doing. Using Pascal's triangle, that pattern, we can fill in all those numbers across the top. So let's continue down this next row. We can get to this point from above or from the left. That's 3. We can get to this point from above or from the left. That'll be 6. So let's skip over the tree. The only way you can get to this point right here is from directly above. It's the only way you can get there is from that spot directly above that has the 4. So that will also be 4. Again, you're not counting blocks you're traveling, you're counting routes that are being followed. So to get here is part of the same route that that got us to the point above that. But now, to get to this point, we can come from above or from the left. So we'll add the 5 and the 4 together and get 9. And to get to this point, we can come from above or from the left. So we'll add the 9 and 6 together and get 15. Down here, we can get there from above or from the left. So we'll add 3 and 1 together. To get here, we'll come from either above or from the left. We'll add 6 and 4 together. So that'll be 10. Who thinks they know what number will go right here? I hear 14. Anyone else have guesses? Eh? You feel comfortable with 14? You said it, right, Marion? You want to bet a pop on that? No, no help from the peanut factory. You're doing it or you're not? Okay, I say yes. And I owe you a pop. Yes. And you owe me about 10, so I'll just take one off what you owe me. What kind do you want? Diet what? Okay, Coke Zero good? Okay. Actually, I think I have a cold Diet Pepsi in the fridge I can get for you right away here. Is that okay? Okay. All right. So now we just continue. 14 and 9 is 23. 23 and 15, 38, and the last row done exactly the same way. 90 different routes could be followed to go from A to B. Find the number of pathways from A to C, but you must go through B. So from A, you have to go to B first, and then you can go there. From there, you can go on to C. So because you have to go to B first, you can only go to the right as far as right where I've shown that. Because there's no backtracking. You always have to be moving closer to B and closer to C. So as you go down, you can only go down as far as those first 2 roads, if you want to call them that, because you have to go to B first and you can't backtrack. So this will be 2, this will be 3, this will be 3, 6 ways to get to B. And then from B, you're going to go to C. So these will all be 6s along here. Again, we're counting the number of routes to follow. The only way you can get to this point right here is from directly from B. It's part of the same path. Same thing to get to this spot here. You're coming directly from B, part of the same path. Same as all these spots going directly below B, part of the same path. There will be 12 ways to get there and 18 ways to get there. How many ways to get to that point there, Sant? Again, so much confidence in your voice. Is he right, Nathan? Yeah. The only way you can get there is from directly above. So that's 12. What about the spot down here, Sant? And you're going to bet a pop on that? Yeah. Yes. Because you can get there from over here as well. From above as well as from the left. But here it'll be 12 plus 18, which is 30. 30 plus 18, 48. Different routes could be followed. Okay? That's it.
That was really loud clap.
You Roger? I've always been there. But like, I'm kind of like coming out from that high. I'm curious with that high.
There's this thing.